finish out chapter 7. We'll see if that
Okay.
hope becomes reality. So I've got a handout for us to look at that kind of goes over part of what we did last time, and it also goes over a little bit of 7.2. But first I want to see if anybody has any specific questions about anything from the homework. Yeah.
Number 4
4 in
in 7.3.
3. This is on page 340. Number 4. So this is one of those problems where very often I'll do this when I'm lecturing. I'll kind of leave something out, and what I'm hoping that makes you do is to go back and actually read through the section. So they talk about an unbiased estimator in this section. And this is kind of going back to what we were talking about before with, remember when we first talked about standard deviation, we got this dude first, and then we took the square root to get the other guy. And if I'm you, I'm kind of like, well, why in the world do we even get sigma squared in the first place? We really seem to always want to have sigma. Well, now we know why. This is a biased estimator, whereas this is an unbiased. And what that really means is, and you saw this back in section 6.4 if you did that work, the standard deviation does not come out to match what it should be when you start taking samples. It doesn't match what it's supposed to be. The variance does. So this is biased because for certain sample sizes, this will be smaller or larger than it really should be if I start taking samples. Whereas for the variance, it'll all kind of come out to be what it's supposed to be in the end. So these will target the actual population standard deviation variance. If I take a bunch of sample variances, they'll actually hone in on the actual variance, whereas these won't. So this does have a purpose to it. That's one of those little definition questions I wanted you to go back and read through to find, and I think it's on, let's see, page, what was that? Oh, that's right. Let me look, I'm not sure where it is. There we go. Oh, what is this? We talked about it a little bit on page 333. This might be one of those that was actually in 7.2.
It's the 69.
Hmm?
Yeah. The 69. 269.
Oh, well, there you go. It's back from section 6.4. Yeah.
Yeah, it's when we did the same.
So on the bottom of page 269, way back in section 6.4, where they first talk about targeting the actual mean or not. But they actually do come back to it in 7.2, which we haven't officially done yet, because I wanted to get 7.3 first. So I always try to only change up the order of the way I lecture from the way the book lays it out when I truly have a disagreement with the way the book laid it out. 7.3's formula comes from a formula we already know. So that's why I want to do 7.3 first. Now, the bad part about that is sometimes there's something in 7.2 that they ask you a question about in 7.3. So now today we're going to go finish out 7.2, definitely, so you have the whole picture. Okay? Okay, so you can go back to section 6.4 and reread what it means to be biased and unbiased. But it's just when you go through that whole process of taking all the samples and taking all the standard deviations, the average of all of them is not what it's supposed to be. But if you do the variances, It is what it's supposed to be. So that's why that's unbiased. Right? All the samples don't throw it off target. They all average out and put it back to where it's supposed to be. For the variance, not the standard deviation. So the low variance dude says, hey, I have a reason to exist. Right? I'm not biased. Leave me alone. So it actually has a purpose. So we'll see later. Actually, hopefully if we make it to these things called chi-square distributions, we have to do first step variance because otherwise the formula won't work correctly. Because the fact that standard deviation is biased, it'll throw us off. So we'll have to use the variance to begin with. Okay, so that was a question that went back to section 6.4. Any other questions from homework? Yeah.
Can you do number 18 and 19?
In 7.3?
Oh yeah, 17.
Oh yeah. So, and again, this is another place I disagree with the book, but I've got to make sure that you guys understand where I'm coming from. I wrote this formula the other day like this, which, just to be a total dork for a second, is the right way to write it. I hate the way the book writes it, but I need to make a point out of that. What did we call this there again? And it makes sense because that's, I say, it's this, give or take this, so this is how much I think I'm off by, right? I say, well, you look about 38 years old, give or take 5 years, you know, just give myself a little cushion of error to allow myself to be off. So this is the error. So in the book, they'll say error equals z sigma over square root of n, and then they'll say x bar plus or minus error. These are the same, aren't they? Just for some reason, they take two lines to say what should be said in one. But they're the same exact equation. So how do you do number 18? They give you output. And the funny thing is, I haven't even talked about how to do this in the calculator, but you should be able to hopefully see what this means. Okay. And there are actually problems earlier than this. Where are they? Oh, they'll be back there. Okay. What do you think this here represents right there? What do you think that represents? So the problem says, express the confidence interval in the form x bar minus e. Because remember, what's the whole idea here? The whole idea here is I get a sample mean, and then I go up and down so much so I think I catch the real mean. So I'm trying to catch the real mean in between the lower part and the upper part. That's what that says, right? So what's this?
The high and the low.
Yeah, the upper part and the lower part, right? That's what that is. That's the actual confidence interval. We are such and such percent confident that it's from this to this. And the mean is this here, right? So how do you figure out what the error is? Here's the mean, 21.12. Here's this guy, 19.853. Here's this guy, 22.387. This is my confidence interval over here, right?
Just subtract 22 from 20.
Yeah. The error must be how much off I am. That's all. How off is this? That's the error. And then just double check. Add that to this. It should be that. This should be right in the middle of these two. Why? Because I add the same thing and subtract the same thing. It should be right in the middle then, right? Go up and down the same amount.
Let's say it again. How do you do it?
So let me give you easier numbers to look at. It might be the numbers throwing us off. If I had a confidence interval that was 0.5 to 0.7. Oh, thanks. 0.5 to 0.7, that's my confidence interval, right? We are 90 whatever percent confident that the mean is from 0.5 to 0.7. Can anybody tell me what my sample mean must have been?
0.6.
Why?
Because it's in between
Halfway.
point.
Where's the sample mean always going to be in my confidence interval? It's got to be right in the
Middle.
middle. So what's right in the middle? 0.6. What must my error be?
0.1.
0.1. That's how far off I was. Now that's the same damn thing, it's just got uglier numbers. But you've got calculators, so who cares, right? How far away is this? 1.267. And double check, is that the same thing? Okay, good. So they did their stuff right. So what is this now? What is that?
That's your error.
The error, because there's my sample mean. How much do I think I'm off by? 1.267 down or 1.267 up. That's how much I think, give or take, 1.267. So how do you write it like this? Sorry, did you know?
No, I was just gonna say, if I subtract the first two up there,
And then divide by 2. Exactly, of course, right? If you subtract these and divide by 2, you should also get the error. Because overall, you can talk about the width of this would be 2e. Because if I go from the mean up error and down an error, how far apart are these two? 2 errors apart, right? I don't know if you guys can get that. But to me, it's just easier to remember the error is how far away one side is from the middle, from the mean. So how would you write it like this? Well, the mean is 21.12 minus the error less the mu less than 21.12 plus the error. So the mean, I am such and such % confident that the actual mean is between this and this. That's what that says. Here's a really funny thing. Do you guys remember from algebra what you call this notation? The notation when you had parenthesis this, comma this, parenthesis here? Interval notation. And we're making confidence intervals.
Cool.
So that's sort of where that comes from. Cool. Who had their hand up? Yeah.
I thought it's the standard deviation away, not like why is it error? Aren't they the same? Are they not the same thing then?
Definitely not. Because the error is not just the standard deviation. I've got to know how many standard deviations I want to go out. And where do I get that z-score from? Why does z-score change sometimes? Why would I want to go out further sometimes and not go out as far other times? What happens if I go further out from the sample mean that I see? What happens?
Your confidence level.
Yeah, it'll change how confident I am about catching something, right?
So is this not a z-score?
There's a z-score part of it, of course. Because if I want to be 90% confident, I would go up and down 1.645 standard deviations, right? If I want to be 95% confident, I have to go out a little further. Why? So that I'm more sure that I caught a specific something. So, maybe I should redo the lecture from yesterday, or from the other day. Because the whole idea here is, here's the idea, because the formula is pretty crazy easy. You just got to plug and chug. The formula, I don't like to teach it that way, but that's all there is to the formula. The formula is this, and you can see the idea in the formula. This is what I can actually get a hold of, right? I get a sample of 88 people, and I find their average shoe size, whatever the hell I'm studying, right? So I can actually get a hold of that number for real. And then somebody says, well, what the hell does that mean about the average shoe size for everybody here? That's what I want to say. I want to know what the average shoe size is for everybody. So then I go, crap, here's my X bar. The real average is somewhere. So if I just go down and up far enough, then I am such and such confident that I caught the real average. And in fact, if I took a really good random sample, the real average should be pretty damn close to this, right? And we see that. If we take a larger sample, good random sample, that's going to make this error go down. I'm going to have to go out not as far as before. Because then I should be even more sure that the real mean is close. Okay. So the z-score is a part of it, of course. Here's the standard deviation too, right? Is everybody cool with that's just the standard deviation now, right? Why is it divided by square root of n?
It's a sample.
I had to take a sample to get the mean anyway. So the minute I take a sample, and I'm talking about sample means, I have to change that standard deviation. So here I am at my sample mean, and just to cover my ass, I say how far up and down do I have to be some level of confidence. So what I mean by that is if I want to be 95% confident, I want to go far enough out that I catch 95% of the information. Because then how sure am I that I caught the real mean then? 95% sure, right? If I catch 95% of all the criminals, how sure am I that I caught a specific criminal? I'm 95% freaking sure. What's the chances he got away? 5% chance, right? That's really what's going on here. We're trying to catch this dude. We're trying to catch him. So I get close. I just say, okay, well, let me go out a little bit, and then I could be such and so percent confident that I caught him. Real quick question. How could you be 100% confident? Never. You'd have to go out infinite, right? You can never be exactly 100% confident. So, and that's why I love statistics, because it's honest. It says just give up trying to be 100% confident. You can't be. So if I want to be 95% confident, if you guys look on your little baby chart, careful. And who remembers from empirical rule, what should this be close to? How far do I have to go out to catch 95% from empirical rule? 2. And what it really is, you're saying that's 90%. What is it for 95%? That's 90%. 1.96. Cool. So I have to go up 1.96 standard deviations and down 1.96 standard deviations. Now, how does this compare to like finding min and max? I think that's what you might be thinking about a little bit. This is exactly like finding min and max, isn't it? 2 differences. It's not always 2 now, is it? I can control how many steps I take. If I want to be more confident, I take more steps. Less confident, I can take less steps, right? And it's not just sigma anymore because I have to take a sample, so I got to have sigma divided by square root of n. But it is a lot like mu plus 2 sigma, mu minus 2 sigma. Isn't that mu plus or minus 2 sigma?
Mm-hmm. Yes.
So now what are we doing? I don't know what the hell mu is. So I use x bar. I don't have to always take 2 steps. I can take as many as I want. I can take it just a little bit and be very unsure, or take a lot more and be more confident that I caught the right thing, right? And it can't be just sigma now because I had to take a sample to get this dude. But they really are the same stupid thing. They really are the same exact formula. One is for individuals. The other one is for samples with a sample mean. They're the same formula, right? Exactly. Maybe. So to put it in the same language, if I take a sample mean and I want to find the minimum and maximum things that I believe the mean can be in, that's exactly what this formula does. Give or take this many steps. Okay. So let's do a quick example here, and then we're going to do some new stuff. So if I took a sample of, I'll do it in English here. Take a sample of 92 stats teachers. We find they have an average. What do I want to say about them? An average amount of coffee intake per day.
So this 7.2 stuff.
Yeah. Because talking about averages, right? 7.2 is going to talk about percentages, proportions. Average amount of coffee intake per day of 2.3 cups. Okay, so far so good, right? This sounds very statisticky, just to make an adjective. We take a sample, we ask them a question, we find an average from that. We know that the standard deviation of the population for coffee drinks is 0. Well, let's make this more interesting. Say it's 1.05 cups. Let me ask you a question. Let me see if anybody can get this. what, before I can use z-scores related to percentages, what do I have to know about my distribution?
It's normal.
Normal. Now think about that sentence I just said. First day of this class, you would have had no idea what I was talking about. But now I think most of us do. So why do I say it's normal anywhere?
No.
Do I have to say it's normal anywhere?
No.
Why not?
Because sample's greater than 30.
Sample size is bigger than 30. I love it, right? That's the central limit theorem. Sample size bigger than 30. That's why that's got to become the new standard deviation there, right? Because I've taken a sample and I'm talking about the sample average. Cool, cool, cool. So the only thing I've left out that we need is how confident we want to be. Create the 99% confidence interval. CI confidence interval from now on. So the great thing about these problems, once you've suffered through your stats teacher desperately trying to make sure the concepts make sense, they are freaking easy, right? We haven't learned any new formulas yet, but it's got to be this formula because I know this and I'm asking about averages, right? So we're going to learn today about making confidence intervals for percentages. So obviously if I'm talking about percentages in my problem, I want a formula that's got a P in it for percentage, right? What do I need to know for this? Do I know everything I need to know? Do I know the sample mean?
Yes. So you don't know
Kick ass. Right. So I know the sample mean is 2.3. I know the standard deviation is 1.05. I know n is 92. How do I get z?
You solve your chart.
Use the z-score chart, right? So if you want to do it the long way, 99% confidence. How much would be out here in the tail?
1% is
0.5.
0.005, yeah, 0.5%, so 0.005. We did this the other day. If you look that up, you'll get negative 2575. I like it. So what's the z-score then? Not a trick question, don't worry. Just 2.575. You don't have to make it negative because the plus or minus are built in, right? So don't throw a negative in there because that sometimes throws people off a bit. Like, what does a plus minus sign do with a negative? Well, you don't need it to be negative anyway, so don't worry about that. So now just throw everything in. The mean, 2.3, give or take, this many steps. So 2.575 times the old standard deviation, 1.05, divided by the square root of 92. Yes, sir.
I'm just a little bit confused, but you're using a sample mean. Wouldn't we be using a sample standard deviation instead of the standard deviation of the population?
Thankfully, in this case, if I know the standard deviation for the population, I'm going to use that, right? Because my sample standard deviation isn't going to be the correct one? No. What you're really asking is, in real life, do we really know this?
We don't.
No. So what this section is doing is building directly off of what we know. What section 7.4 is going to do is say, oh shit, I normally don't know this. I normally only know S. And then we have to learn something new. Not entirely new, just a little new, right? So that was a good question. Yes, sir.
Yeah, that 0.005. That's right.
So if there's 99% in there, there must be
Right.
1% out there,
Okay.
which means half of a percent down here, which is a decimal, is 0.005.
Oh, okay.
Or again, the 99%, isn't that in your little baby chart?
Yeah.
And you can just find a 2575. Cool. Okay, okay. But you have to know how to do this in case your evil instructor wants a 96% confidence interval. And that's not on your little baby chart. So then you'll say 4%, 2%, look up 0.02, get the z-score. You have to know how to do that little process, right? So this, what was my suggestion on what to do first here?
The error.
The error. And has anybody got that for me?
282. 0.282.
0.282? So are you guys getting that for the error? So now I just take 2.3 minus that and 2.3 plus that, right? To get my interval from 2.3 minus this to 2.3 plus this. Oh, 0.282 you got. Then why are you adding that? Oh, this whole thing is 0.282.
Oh, okay.
So it'll be 2.3 plus this, 2.3 minus this. Yeah, be careful. Don't throw him into it again. Yeah. Okay. So then you get roughly 2 here, right? 2.018 or something. What is it?
Yeah, 2.
2 roughly. To 2.582. So from 2 to 2.6 cups of coffee a day. So somewhere I am, how do I say this then? I am 99% confident that this interval, 2 cups of coffee to about 2.6 cups of coffee, catches the real average cups of coffee. So I'm not that big on semantics. It's a little wrong to say what I'm about to say, but I really don't care because it's the idea. So there's a 99% chance that the real average cups of coffee that stats teachers have is between 2 cups and 2.6 cups. Right? Semantically, that's not right, but I don't care. It's fine. The math is still there. How are we doing on that? Is that semi-understood? So I mean, this is what stats is. Freaky ass concepts. Okay, this huge concept. You have to kind of understand a little bit, but then the actual work, easy. Right? Just plug and chug. Right? The more you understand the concept, the more you know when to use the right formula. Okay. So let's say that I want to be, so here's my formula again. Let's say I want to be within, let me see if I can make some, let's say within $100 of the real average income for teachers at Grossmont. So what we're about to do, if any of you are going into business, we're about to do something called a feasibility study, which is it feasible to even try to do this analysis? Do I have the resources to do what I need to do this, right? So can anybody hazard a guess about what the hell that has to do with this? I want to be within $100 of the real income. No, you got to be careful. Within 100 actually means I could be up 100 or down 100. So don't cut it in half. There's no need to be in half. If I said I want to guess your age within 5 years, I could be off by 5 years up or 5 years down. What part of this is within? What part of this is how much I think I'm off by? The error. Good. So this guy is the error. That's what I want the error to be, right? So they have to tell me what the standard deviation is, and I have to kind of know how confident I want to be about this. So let's say I want to be within $100 of the real average income for Grossmont students at a 90% confidence. It is known that sigma is, the standard deviation for income at Grossmont is, oh, what's going to make sense, Jeff? $6,148. Not that I know that what all the incomes are at Grossmont College, but All right, so how are we doing so far with what's going on here? I have to know how confident I want to be, because that affects my z-score, right? That tells me how far I want to go. What I really want to know is how many instructors must I sample? So can anybody tell me right there, just reading that, what's the letter that I don't know? The letter that I want to know? N. I want to know how large my sample has to be. Do you see why this is a feasibility study? If N comes out to be 20, sweet, I can talk to 20 people. If N comes out to be 3 million, there are not 3 million teachers here, so it's not feasible then, right? Do you kind of see what I'm saying? This is a whole thing about, well, boss, I know you said you wanted to be within this, but it's impossible. So can you change something, right? So here's the thing. Let me do a little bit of algebra first, because we have to figure out how to solve for N. So this would be a problem where they tell me the error. I know the error, and the formula for the error is here. Very extravagant Z. There. Somebody help me out now. There's very few moments in this class where you have true algebra. Here's one of them. How do I solve this for N?
Multiply by n on each side.
Multiply by,
N.
because the N is in the bottom, that sucks. Let me get it up. So multiply by the square root of N. And then divide by E, right? So don't they really just change places? That's some nifty shortcut to learn from algebra. So divide by E, so it just goes down there. So I end up with square root of N equals Z sigma over E. Is that cool? You guys see that? The square root of N multiplied up, the E divided down. And of course to solve for N, I just have to square both sides. So there is a formula. No, Jeff. For figuring out how large of a sample it's going to take to be within whatever amount. So what am I not given directly in this problem that I need for this formula? The z-score. I'm given it indirectly, right? I know that the sigma is 6148. I know that the error is 100. That's how much I want to be off by at most. And the z-score, what is the z-score for at 90%?
1.9.
The one you're saying earlier.
1.645.
Cool. I thought you just had, you could see it coming. So now you just plug and check again. Right, so this is just purely a plug and check problem now. It's kind of nifty. So if I throw in there my z-score 1.645 squared, my standard deviation 6148 squared, and my error 100 squared, this is probably going to come out to be quite a lot. Thinking like 110,000, 120,000. I don't know. Was it
10,000.
so it's off by a factor of 10, Dan. Was it not again 10,000 something?
228.
Oh, so it's off by just a factor of 2. 228?
No, 10,200.
Oh, 10,228. Okay, thank you. Are you guys getting that also? This is actually one of the easier formulas to plug stuff into. You just gotta plug square, divided by this squared, bam. Right, just get it directly. So make sure you can get that. Did it come out to be 10,228 exactly, or what it was?
.207.
Oh, so was it 10,228.207? What do you think if I need at least this many to be within 100, if I got 10,228, would I be within 100?
No.
No. I need at least this many. I can't get 0.207 person, so you always round this up to the next whole number. It only makes sense. I can't get 0.207 person, so let me get a whole person to cover that. So that's 10,229. So is this feasible? Are there 10,229 teachers at Grossmont?
No.
No. Right? It doesn't cover the entire state of California. So this would not be feasible. I can't get within $100 of the real income by taking a sample like that. Because what it's really saying is that I have to take all the teachers anyway, and then I know the real income perfectly. So this is saying it's not feasible to do it with the sample. I can't.
What exactly the right answer?
10,229. Yeah. Okay. So, yeah.
One small question about why you pick 1.645 as your z-score. If you're looking for a range of 90%, why would you add in that extra 5% for the tail?
I didn't add anything.
You didn't
If
add.
I want to be 90% sure that I go up and down so much and catch the right thing,
Right, alpha's going to be 10, alpha 2 is going to be 0.05.
yeah, this is 0.05.
Right, so why would I go for a 95% confidence interval?
I didn't.
You found 95.
I did. Yes, I did that. If I want 90% in the middle,
Right.
can I look up 0.90 in the chart and have it mean anything with this problem? Because the chart only understands areas that are totally below. So if you want this Z-score, which is the one that, with this guy, they bound the middle 90, how much is actually below him? 95%. Did I make it a 95%? No. There's a 90. What do I need to look up, though, for him? The total below him, 95. Don't let that throw you off. When I'm talking about confidence intervals, that's the area in the middle. Is the chart set up to understand that? No. So if I have to use a chart, I'm going to have to adjust things, right? To me, it's always easier for me just to look him up because it makes more sense. If that's 90, that's definitely 5%. There's no question, right? And when you look up 0.05, you get the negative 1.645, and the other one's got to be the positive 1.645. Cool. How we doing? Because I know if I say 95% and you look up 0.95 in the chart, that's wrong. You'll actually get a 90% confidence interval. That chart does not understand areas in the middle. It only understands areas totally below a z-score. Okay. So taking a step back to 7.2. So we're going to get two little formulas from this section, just like we got two little formulas from section 7.3. Somebody remind me, for a binomial, which is the kind of thing we'll have here, because we're talking about percentages of people. So there'd be a problem like, I take a sample of people and 44% of them will vote for Mitt Romney. Find the 90% confidence interval for the total number, the percentage of everybody that would vote for Mitt Romney, right? That kind of problem. So when 45% vote for him and 55% at least won't say they vote for him, right? So there's your P and Q. So these are binomial types. Remind me, what's the mean for that kind of thing? N times P. And what's the standard deviation?
Square root of Q.
I love it. Now, one little thing I have to address is this symbol, of course, is for a what? As opposed to X bar.
Population.
That's for a population, correct? So this P is actually the percentage of the population also. So that P must also be a population thing since they go together. So when I take a sample, so for example, if I took a sample, if we sample 804 people and find 391 of them will vote for Mitt Romney. Can somebody just tell me what the percentage is from the sample that I see? Now, this is a question outside of statistics. It's just a percentage question. Can you calculate the percentage that I see from the sample I took?
48.
And how'd you do that?
Just divided 391 by 804.
391 divided by 804? We can't, why, can somebody tell me why I can't use the letter P by itself for that? Because what did P represent? The percentage of the,
Population.
and this was a sample. So just like the X has a bar on it, and that means it's an average, right? I got to put a little piece of clothing on my P. P, you guys, I love this. P hat is the percentage that I get from a sample. It does sound like something I never want to wear. Here, wear the P hat. No, I don't think so. But does it make sense? If you see a little hat on P or Q, that means it came from a sample.
Can you say what P
P hat is the percentage from a sample. Just like X bar, it's got a bar on it. That's an average from a sample. P hat, it's got a little hat on its head. That's a percentage from a sample. Cool. How are we doing so far?
Is it from language or something?
Hmm?
Is it from the language or not? French.
Oh, is it from French? I don't know.
Yeah,
Can't
it
speak to
is.
that. Oh, it is? Okay.
Yeah.
So it's P chapeau.
No, that's
No?
That's
It's my one French word I happen to know at the moment. Okay, and so you got, what'd you get for that again? I'll always take it out. I'll tell you, it's just like standard deviation. Percentages, always take it out 3 places. So what do you get?
0.486.
486? Okay, cool. So then what would Q hat be?
It would have to be the differences.
Yeah, 1 minus 0.486, right? Just because they're wearing hats doesn't mean they don't have to add up to 1 anymore, right? They can wear whatever the hell they want to. They still have to add up to 1. So this would be 0.514. Okay. So, the formula that we use for this, I at least wanted to start there just to show you what P hat itself was. The formula that we use for this sort of comes from the idea, again, we'll start here again. And we'll say, okay, I don't really know the mean. And in fact, in this case, if the mean is NP, what are we going to have to use?
P hat.
P hat. That's like the sample mean would be NP hat. Are we cool with that? So do we have the mean? No, we have NP hat. And again, this is derivation of the formula, so I want to show you where this formula comes from. Plus or minus z, and what's sigma? And I don't know P and Q, so I actually have to use P hat, Q hat. So it is sort of like an S, sort of like a sample standard deviation. Since they have little hats on them, I'm telling people, oh yeah, this is my sample standard deviation here, right? Because I got my information from a sample. That's why I put little hats on them. How you doing so far? I mean, and again, this is the derivation. This is not the formula yet. Because what I really want here is just P by itself. Cool? I really just want P by itself here. So I can say it's 60%, give or take 5%. So I want a percentage, give or take something, right? So how do I do that? Now here's where you're going to have to just go with me. I don't want to get too technical here. I just want you to, I am kind of approximating the average of the population, right? I'm trying to capture him. So if I divide by n, I don't want n there, do I? Divide by n. And if you want to do your two sides thing, I kind of appreciate that. When I did this last semester, somebody said, how can you divide by n? You don't have another. Yeah, I do. It's sort of there, right? It is there, so don't worry about dividing by n. I'm allowed to. Here, I'll do this part. That's easy. So I get P hat. Now what happens here? Can I just cancel those n's out?
No. You get n.
Hell no. Why not? One of them is in a
Square root.
square root. Are you guys cool with if only the only way that it can operate with roots is if both things have the same root, in this case a square root. So how can I rewrite n so it's the square root of something? What is n the square root of?
N squared.
N squared, I love it. Thank God. I'm always worried somebody's like, I don't know. But that's all it is. It's just square root of n squared is n. Right? And I still have on the top z, n, p, q. Hats. Now what can I do?
You can cancel an n out.
I can cancel one of the ends out, right? So one of those ends goes away. So here's what my formula looks like at the end. Make one big square root over everybody. What's left alive on the top?
N and p.
P hat, Q hat. The n died, right? Over n. That's the formula for section 7.2. That's how to get a confidence interval for a percentage. So if I take a sample and find a percentage from the sample, is that going to be the real percentage of the whole population? No. I'm going to give or take this much to cover my ass. All right, so let's try a problem now. So now this is just another formula that can be on your formula sheet. Oh, you're okay. Good. So if we take a sample of I don't know, 907 stat students, and find 852 don't like confidence intervals. Right? So now I want to find a confidence interval. Let's say find the 98% confidence interval for the true percentage of all stat students who don't like confidence intervals. Right? So this is the language you're going to hear in these problems. They give you a situation, then they're going to tell you create this confidence interval. The funny thing is, it sounds like they didn't give me enough information if you first look at it. Because for the other problems in 7.3, they have to give me a sample mean, a sample size, they have to tell me what the standard deviation is. They tell me all this stuff. Here they gave me two numbers in the confidence. Why is that true? Because look at the formula. Once I know P hat, I know Q hat. And P hat and Q hat are in there. I mean, I don't have to know much. It's kind of nice. How do I get P hat?
852 divided by 907.
Yeah, it would be 852 divided by
907.
907. So just remember your part divided by whole. This obviously can't be bigger than 1, right? So don't. Then your Q would be negative, and then your square root would freak out. So don't do that. And what do you get for that going out 3 places?
0.939.
9 who? 939? So what's Q hat?
0.061.
0.061, cool. Good so far? And what's the only other thing I really need for my formula? Because I know n. N is what? 907, beautiful. Not 852. N is always the total, right? What's my z-score going to be for 98%?
2.05.
Mm-mm. So how do you do that? Let me see if you guys can do it. Don't say anything out loud. Try to figure out for a 98% confidence interval, what would that z-score be? How far out do I have to go?
Negative 2.31.
Almost.
2.325.
0.6. 2.32.
I love it. So this will be, this is 2%, so this is 0.01. And the closer you get to 0.01 should be 2.323.
3.
Officially it's actually 2.326, but from our chart, the best we can do is 233. That's fine. If you say 2.325, that's even better a little bit, but 233 is perfect. Now I've got everything I need, don't I? This little tiny formula is awesome. This thing kicks ass. I don't really need that much. So to plug everything in, here's P hat, give or take, Z. What does this piece kind of act like then for this problem? This piece here? No, just that piece by itself. That acts like the standard deviation. And remember, for the x bar formula, doesn't the x bar formula have sigma over square root of n? Doesn't it have an n on the bottom?
Mm-hmm.
And so does E. So in another sense, I could have just skipped all this crap and just said there's an n on the bottom, just like there. But you know me, I can't ever do that. So now I just got to throw everything in here. What was p hat? 0.939. Give or take 2.33. Square root of 0.939 times 0.061 divided by n. 907. Now let me do this. This is always where things kind of go a little haywire with plugging it into the calculator. I don't blame you. It's not the prettiest thing in the world. Those of you who have the newer TIs or have gone and updated your TI online and your square root symbol actually grows to cover everything, you're going to have a little easier time with this. The rest of us are going to have to, when they open that parenthesis, you don't want to close it so you're done. If you close it here, oh shit, you're outside of the square root symbol now. That's the big thing that's the most, that's the mistake that's made the most. So I'm going to do this up on the board to show you how to put this in the calculator correctly. Yeah.
How many decimal places do you want us to go out for the error? 4?
Normally, you make the error the same as what you're given here, and we normally go 3 here, so 3 is fine. So I'll do this up here, and then I'm going to let you guys work on a little handout together. And then if we have any time left, we'll try to get into the next section a little bit. So here's the problem. Okay.
I have a question.
This way.
Why didn't you close the 12.939 to 0.061? Why didn't you close it on top?
If I close it here, then I'm out of the square root. At least in the calculator. On the board, why can we tell that I'm not out of it yet? Because I can extend that. So that's what I'm saying. Those of you with the updated TI, it actually extends the square root symbol. That makes a shitload of sense, right? But for the rest of us, they just have a stupid little square root symbol like this. Let me put this error in, right? Just like before. So 2.33 times the square root. See, that we get that. We don't have a little bar that goes forever. So I don't want to close that parenthesis. If I do, the calculator thinks I'm outside of the square root symbol. So I want to put in there 0.939 times 0.061 divided by 907. And then I do closing that. See that? So now I've got the whole thing inside the square root. Is that, do you guys see the problem that you have to be careful about? And there will be other formulas that have similar issues with square roots later that we have to be careful about. So my error then looks to be about that. So my error looks to be, I really do dislike this room. Let's see. So I get 0.939, give or take. Oh, thank you. I think everybody saw that. Give or take the 0.019, right? And now you just have to, just like before, subtract it, add it, and see what you end up at. So isn't this like 94%, give or take 2%? Do you see that? So wouldn't this be like at the bottom of the screen, if this was a report on the news, they'd say 94%, and at the bottom would say plus or minus 2 percentage points, margin of error. That's where the hell the margin of error comes from. Right there. The things they don't tell you. What confidence level did they use? They never tell you that. They never tell you that. Of course, you guys before this didn't know to even look for it. And they never tell you, really, mostly on the news, they don't tell you what the sample size was. Right? If the sample size was 2,000, okay. If the sample size was 80, well, it's okay, but you could have done better. Right? So what do we get here? We get
0.920
920
to 0.958.
Cool. So about 92% to 95.8%. So we are 98% confident that the true percentage of all stat students who don't like confidence intervals is between 92% to 95.8%. Which I hope is not true, but it's all made up data at the moment, so what the hell. So let me do this. Let me give you the handout, and then I can answer any specific questions. In 1 second. Let me give this out, and then I'll help you out.
I'm not calculating that, I don't know why.
So this is not a quiz or anything. You can work on it together with somebody else. Did you hear from Kate?
Yes.
Could be good. I couldn't make it myself, then I try never to turn down free food.
Exactly. Thank you.
Okay, sir. Oh yeah, you missed the point. Yeah. Oh. Oh yeah, I do actually. If anybody needs a Z chart, I've got a few. Oh, it's all messed up. Robert, are you here? Robert? Kristen. Joseph. Russell. Chantel, there. So notice how in the question it says find the 90% constant for the true proportion. So I know I'm gonna have to use one for the P for proportional percentage. This says find it for the true mean. So it's gonna be a giveaway. I mean it's gonna be I know I've gotta use the one with key in it if it's a percentage of proportion.